Hello everyone, welcome to this module on Advanced System Design Principles and Trade-Offs. So, when you use a messaging app or a streaming platform, you probably don't think about what's happening behind the scenes. But every time you send a message or watch a video, the system is making hundreds of decisions. Decisions about speed, reliability, and how data is handled across servers. These decisions are rarely simple. Improving one thing often affects something else, and engineers constantly have to weigh the trade-offs. In this video, we'll explore what those trade-offs look like, why they matter, and how real-world systems manage them. So, first up, GAP theorem. This is fundamental in distributed systems. GAP stands for consistency, which means all users see the same data at the same time. If one client updates something, everyone sees it immediately. Availability, which means the system always responds to requests, no timeouts. Partition tolerance, which means the system continues working even if some servers can't talk to each other due to network failures. But here's the catch. You cannot guarantee all three at the same time. You can only have two of the three. Why is that? Imagine a distributed database split across two cities. Now suppose the network between the cities goes down, a partition occurs. If you prioritize consistency, both cities must agree on every update before responding, but they can't communicate, so requests are delayed or rejected, reducing availability. If you prioritize availability, each city responds immediately, but some users see stale or conflicting data, reducing consistency. So during network partitions, you must take a trade-off. You can't have both. For example, take Cassandra. It's an AP system. It prioritizes availability and partition tolerance. Millions of users can read and write at the same time, but some reads may be slightly outdated. Next, let's talk about scalability versus reliability. Scalability is the system's ability to handle more users, more traffic, or more data without slowing down. Reliability is the system's ability to keep working correctly even if parts of it fail. These often conflict. For example, if you had more nodes or shards to scale horizontally, you increase potential failure points. In a real-life notification system, users might be split across multiple servers or shards to handle large traffic. This improves scalability, but now you have to coordinate across shards to maintain event ordering. If one shard fails, only that segment is affected, but monitoring failover becomes critical to maintain reliability everywhere. Another trade-off is latency versus consistency. Latency is how fast the system responds to user actions, while consistency ensures all clients see the same data at the same time. High consistency often increases latency because updates must be confirmed across multiple nodes. Low latency allows immediate responses. Some clients might temporarily see stale data. For example, let's say in a messaging app, prioritizing low latency, the sender sees their message immediately, but other recipients may see it a few seconds later. By prioritizing strong consistency, all clients see the message at the same time, but the system introduces a small delay to confirm updates. Many large systems use eventual consistency. Temporary differences are allowed to keep the system fast. Now let's combine these principles in a real-world system like a high-scale messaging platform. GAP decision. The system must choose whether to prioritize availability or strict consistency. AP systems optimize speed and uptime. CP systems optimize order and accuracy. Shard for scalability. Users or messages are split across multiple nodes, each shard handling a subset of users to balance load. Queues and caching. Asynchronous message queues and cache reduces latency and prevents servers from getting overloaded. Messages are delivered efficiently without bottlenecks. The goal is a system that's fast, reliable, and scalable, knowing that no system can be perfect in all areas. Some additional advanced considerations include replication strategy. Synchronous replication ensures consistency but increases latency. Asynchronous replication improves speed but may temporarily serve stale data. Failure handling. Systems must gracefully handle node failures with retries, failover mechanisms, and monitoring. Trade-off evaluation. Every decision should weigh expected load, user experience, and failure probability. To sum up, gap theorem, only two of the three properties can be fully guaranteed at a time. Scalability versus reliability, adding capacity brings complexity and risk. Latency versus consistency, faster responses may compromise strict accuracy. Physical systems, sharding, queues, and caching help balance trade-offs. Advanced system design is about making informed compromises where each trade-off is deliberate, measurable, and aligned with the system goals. In the next module, we'll explore client-server architectures and scaling strategies and see how these trade-offs are applied in practice. We'll look at how messaging apps, streaming services, and collaborative platforms implement these principles at scale. Thank you for watching, and I'll see you in the next video.